Welcome to your business calculus lesson 2.2. We're going to take it to the limits one more time. Okay, so we've got the function f of x equals x plus 2 if x is less than 3. Okay, so for this part of our domain, the rule is x plus 2. And then at x equals 3, the function equals 2. Okay, so there's the 0.32. And then for x greater than 3, so this part of our domain, the rule for the function is negative 2x plus 11. All right, so we've talked before kind of about when we were determining the limit, what's happening from the left, what's happening from the right. We're going to formalize that a little bit. There are one-sided limits. The notation, the limit as x approaches 3 with a little plus there of f of x equals 5 is meant to communicate the same information as the limit as x approaches 3 equals 5, with the exception that only x values larger than 3 that are to the right of 3 are considered. So x will be approaching from the right. So we're talking about values here. Since we want them close to 3, they're going to be these values right here between 3 and 4. And so we're going to look at what happens as we go to the right and get right up close to 3. So let's map that onto our function. Okay, so now we're not just going to, as we're going to the right, we're going to see where the function goes. So as we go to the right, if we're staying on the function, we see that it's approaching the function value of 5. Okay, so let's see what happens on the left side. So we've got the limit as x approaches 3, and then a little negative sign that's red, x approaches 3 from the left of f of x is 5, means that the limit of f of x as x approaches 3 from the left is 5. So we go to values to the left of 3. So these right here, right before we get to 3, let's map on up to our function. And as we move closer and closer to 3 as far as x goes, to stay on our function, we have to go up, and we are approaching the value of 5. All right, since the two sides, the limit as x goes to 3 from the right and limit as x goes to 3 from the left are both going to 5, then the limit of f of x as x goes to 3 is 5. Now, notice this is one of those cases where f of 3 is not equal to the same value as the limit. F of 3 is 2, but that's okay. All right, sometimes when we are working with functions and trying to find the limits, remember, you can plug in values if you're given the function itself and see what it reduces to, the value for x that we're approaching. But sometimes you're going to get what's called an indeterminate form, and it's ambiguous. We need to work a little more, re-express things to actually determine what the limit would be. The ones you're going to encounter the most are 0 over 0 and infinity over infinity. In other words, if you try to evaluate a limit by direct substitution, plugging in and get 0 over 0 or infinity over infinity, all you know is that you know nothing. Maybe the limit exists, maybe not. You need to rewrite the expression to find the limit or to determine that it does not exist. Other indeterminate forms are 1 to the infinite power, 0 times infinity, and infinity minus infinity. Okay, so what we're going to do is we're going to look at a few examples, and we're going to talk about some of the ways that you can re-express functions using algebra. Okay, so we want to know the limit as x goes to 2 of x squared minus 4 divided by x minus 2. All right, so let's try direct substitution. We can go ahead and plug in 3. So if we do that, though, we're going to get 4 minus 4 is 0 on top, and 2 minus 2 is 0 on bottom, and oh no, that gives us an indeterminate form. So, okay, we're just going to go to plan B. We're going to see if we can re-express x squared minus 4 over x minus 2. Now, one way you can always try to get started is by factoring the numerator and, if possible, the denominator. If that lets you cancel things out and progress from there, awesome. If not, we're going to talk about some other things you can try. So X squared minus 4, that is a difference of two squares. So x plus 2 times x minus 2 is a great re-expression of that little binomial. And x minus 2 is just x minus 2. And so our x minus 2 on top cancels with our x minus 2 on bottom. And so we get x plus 2 over 1, which is x plus 2. So now we can find the limit as x goes to 2 of x plus 2. 2 plus 2 is 4, so that's awesome. And that means that the limit as x goes to 2 for x squared minus 4 over x minus 2 is 4. Okay, again, if f of x is x squared minus 4 over x minus 2, then the function would be undefined at 2, but the limit exists. The function would be approaching 4 from the left and from the right. All right, so let's look at the limit as x goes to infinity of 7x squared minus x divided by x squared minus 1. Okay, well, we'll do direct substitution. We'll think it through. You could pick a really big number and put it in and see what happens. But what's going to happen is you're going to get huge number on top and huge number on bottom. So infinity over infinity. So that's an indeterminate form. So we could try to factor. They both can be factored. We get x times 7x minus 1 over x plus 1 times x minus 1. There's nothing to cancel there. So that doesn't really work. So we're going to go to plan C, and we're going to divide each term in the numerator and the denominator by the largest power of x. So if we do that, 7x squared divided by x squared is 7. And then minus x divided by x squared reduces to 1 over x. Onto our denominator. X squared divided by x squared is 1. And then minus, and then 1 over x squared is 1 over x squared. Okay, so now as we do the limit as x goes to infinity of this expression, the x's will get huge. 1 over something huge goes to 0. So we're going to have 7 minus 0 over 1 minus 0. 7 over 1 is 7. So the limit as x approaches infinity of 7x squared minus x over x squared minus 1 is equal to 7. All right. Now we're going to find the limit as h goes to 0 of the square root of 4 plus h minus 2 over h. So if we try direct substitution, you're going to get the square root of 4, which is 2 minus 2, that's 0. And then you're going to have 0 on the bottom. So yeah, again, we have an indeterminate form. We can't really factor this. The dividing by the highest power of h thing, it's not really a polynomial, so we won't do that. So we're going to go to plan D. All right. What we're going to do is we are going to rationalize the numerator. See that there's a square root in there? We're going to rationalize it. And the way we rationalize, remember, is that we multiply by the conjugate. We want to multiply by the expression that looks very much like the original, except that we're going to have a plus instead of a minus. Well, if we do that to the top, we have to do that to the bottom. So we've got the square root of 4 plus h minus 2 over h, and we're going to multiply top and bottom by square root of 4 plus h plus 2 over square root of 4 plus h plus 2. So this is the conjugate. The square root of 4 plus h plus 2 is the conjugate of the square root of 4 plus h minus 2. All right, so remember, the cool thing about conjugates is that when you FOIL them out, the middle terms always cancel. That's why you have to have one minus and one plus. So you can use the conjugate shortcut here and just do square root of 4 plus h times square root of 4 plus h is 4 plus h. And then minus 2 times 2 is 4. On the bottom, we've got h times the square root of 4 plus h plus 2. Hold off on trying to distribute that or anything, because if we can cancel, we're going to want that h on the outside. All right, so 4 plus h minus 4 is going to be h. So we have h over h times the square root of 4 plus h plus 2. And so that's going to, the h's are going to cancel, and we're going to be left with 1 over the square root of 4 plus h plus 2. Now we're going to find the limit as h goes to 0. So if we do that, we're going to get the 1's just going to be 1. And in the denominator, we're going to have square root of 4, which is 2, plus 2 is 4, so we get 1/4. So that means the limit as h goes to 0 of our original expression is equal to 1/4. Okay, that's awesome. Do what you can in your problem set, and then come to class ready to work and ready to ask questions, and I will be ready to help. Thank you for watching the video. I hope you have a great day.